In this video, we're going to talk about three related electrophilic aromatic substitution reactions known collectively as halogenation. So these are reactions that allow you to add a halogen substituent to an aromatic ring. So the three that we're going to talk about are bromination, chlorination, and iodination for adding bromine, chlorine, and iodine respectively. Okay, so since it's the one that we talked about in an earlier video, let's begin our discussion with bromination. So if you recall, if we have benzene and we treat it with bromine, Br2, no reaction will happen. And you now understand that the reason is because benzene is aromatic and it's too stable and it doesn't want to give up that stabilization energy to react with the bromine. But that's actually just because bromine isn't electrophilic enough. If we can do something to the bromine to make it more electrophilic, then a reaction can happen. And what we need to do is to add a catalyst. In this case, we're going to add iron tribromide. And if we do that, then the bromination reaction can occur. We will add a bromine to the ring, and then the byproduct is going to be an equivalent of HBr. Okay, so the question that we want to understand is, why does adding this iron tribromide catalyst make this reaction occur? Okay, and what is happening here is that the iron tribromide is activating the Br2 to make it more electrophilic. So here we have Br2, and because this is just two bromine atoms bonded together, this is not it's not a polar molecule at all, right? Because each bromine is equally electronegative, and so they're both tugging on the electron cloud equally. All right, so just not an electrophilic enough. Okay, not electrophilic. Oops, not electrophilic enough. Okay, but if we can treat this with iron tribromide, what can happen is that the electrons from one of the bromines can actually react with the iron, okay? And that's because iron tribromide is a Lewis acid. All right, so recall from general chemistry, a Lewis acid is something that can accept an electron pair. All right, so iron tribromide is a Lewis acid, and it's going to accept an electron pair from one of the bromines, which is thus a Lewis base. And when that happens, we get to a complex that will look like this. Okay, so one of the bromines has been attached to the iron. Now we have to add in some charges here, okay, because we've done this reaction. And so we're going to put a negative charge on the iron because it's gained an electron pair, and we're going to put a positive charge on bromine because it has donated an electron pair. Okay, so now we've got this much more polarized species. Now the thing to understand is that these charges we're putting on are simply formal charges. If we were actually to look at the electron cloud of this whole complex, right, which is just one cohesive electron cloud, what we would actually find, what would be a more accurate description, is that we would find that this end of the molecule is more positive and the other end, way out on the other bromines, is more negative. Okay, so we put the positive charges on those atoms just for formal electron keeping, but this is going to be the electrophilic site. Okay, so this is going to be the atom that a nucleophile will add to. All right, so now we're ready to bring in our benzene into this situation. So let me now draw in the benzene, and I'm going to redraw this complex that we just formed. Okay, and I had better put in my charges so that we don't lose track. All right, so now we're ready to do the first step of the mechanism involving the benzene, which is the addition of the pi cloud to that terminal bromine. and then this bromine-bromine bond is going to be pushed onto the bromine. So what you can think of is that this whole FeBr4 complex is actually a leaving group, right? So the benzene is displacing this whole thing from that bromine, okay? So if we were just to try to react with Br2, this wouldn't be a good enough leaving group, but by binding it to iron, it becomes a very good leaving group, okay? And so once we do that, we get to this cationic complex that is very much like the one that we saw in the last video, where we're going to have this cation that is then stabilized as part of that dienyl system. Okay. All right. Now, let's remind ourselves that this intermediate here is really quite stable, and it's stable because it has a number of equal resonance forms that we could draw. So we could, for example, draw this resonance form, right, where we place the cation at this position, right? So that would be if we were pushing the electrons like that. But there's another one too. We can have the cation also at this position, right? And that is if we imagined pushing those electrons down, all right? Now, so these, again, these are just resonance forms, so these aren't reality. The reality is the combination all of these forms, and so it would probably be more accurate for us to imagine all of these in the following way. Okay, so if we did sort of a not quite full donut there, and we imagine that that positive charge is spread all throughout those 5 carbons, and then here we've got the bromine attached to that carbon, right? So that's sort of the intermediate we got. And now remember, in terms of energetics, this is a relatively stable intermediate in the sense that that cationic charge is spread out over a number of different 5 total carbons. So that's good, but remember that we've had to lose aromaticity to get there. So it's actually still very high in energy. And remember what we learned about in terms of electrophilic aromatic substitution reactions, the molecule wants to regain aromaticity. So this isn't going to wait around for a bromine or other nucleophile to add to that cation. What's going to happen is we're going to eliminate this proton, which is going to happen from this iron tribromide anion that was the leaving group that we displaced. Okay, that we displaced right here, right? So that iron tribromide leaving group is now going to serve as the base to deprotonate. We get that electron pair back, and then that's going to reform our aromatic ring. Okay, and there we go. There's our brominated benzene, and what's left over here are 2 things. So we're going to form an equivalent of HBr, okay, and we're going to regenerate our iron tribromide, which that's what makes this a catalyst, because it can go off and activate another molecule of bromine, and we can keep going around the circle. Okay, so let me just zoom out slightly there so we can get the whole thing in our view. All right, so just to recap, we first need to activate the Br2 with the iron tribromide. That gives us this activated complex, which is highly electrophilic. The benzene can then add to that bromine, displacing the iron tetrabromide anion. That gives us this stable bromine cation intermediate, which then gets deprotonated, and we get to our aryl bromide. Okay, so the key part here, or the unique part here, is that we're generating a highly reactive bromine electrophile, which, at least conceptually, we could think of as a Br+ type of situation. All right, so that's bromination. let's talk about the next reaction, which is chlorination. Okay, so the only thing that's different here is that we're adding chlorine to the aromatic ring instead of bromine. And it turns out that this is essentially exactly like bromination, except that instead of Br2, we're going to use Cl2. And then for the catalyst, we're just going to use iron trichloride. Okay, and that accomplishes the exact same thing in terms of adding chlorine to the aromatic ring. Okay, so the mechanism is exactly the same. We don't need to go through it. All you have to do is go look at the one we just looked at and just replace chlorine for bromine in every case. Now the only key here is that you need to have your catalyst have the counter ions that are the same as the thing that you're trying to add. So if you're trying to chlorinate, you need iron trichloride, and if you're trying to brominate, you need iron tribromide. And that's because if you use iron tribromide with chlorine, you're actually going to scramble the two, and you're going to get a mixture of chlorinated and brominated products, which is not going to be useful. So you just have to have those matched up. But if you do that, then everything is good. Okay, so then the final reaction that we're going to quickly talk about is going to be iodination. Okay, iodination. And conceptually, this is just like chlorination and bromination. Okay, so we're going to add I2. And what we need to do is add something that's going to generate the equivalent of an I+, right? So a highly electrophilic iodine. Now, there's a number of different things we could do, but for iodine, what we really want is an oxidant. We want something that's actually going to fully take away an electron pair as opposed to just polarizing the molecule. So the one that we'll learn is copper 2 chloride. There's a number of different things that we could use, but this one will suffice. And if we treat this reaction then with copper dichloride, we will be able to iodinate our benzene ring. Now, we're not actually going to go through the details of what specifically is happening when we mix these two together. It's more details than we care about. All you need to know is that this is generating the equivalent of an I+. Okay, so what we could draw mechanistically here is, and so this is going to look exactly like all of the other two mechanisms. We generate I+, okay, and then the aromatic ring can attack that I+ to give our familiar intermediate. Okay, and then we need some base, and the base could be a number of things. We'll just use I- for simplicity. I- is going to deprotonate, which will then return our aromatic ring, and there's our iodinated product. Okay, so that's basically all there is for bromination, chlorination, and iodination.